Welcome to note set number 2, where we're going to talk about continuous time signals. So remember, these are the things that are going into a system, and we talked about continuous time versus discrete time. So we're going to focus on the continuous time here. So like I said before, continuous time signal is just a function. So using some math notation here, it's a function f of t, where t ranges over the real line. So we plot it, show it on a plot, f of t versus t, and how it varies with time represents the nature of that signal. Now we have some very special ones that show up an awful lot, and this is called the unit step function. Unit, well, let me back up and say step, because it comes along and then does a step, and unit because it steps up to 1. So at time equal to 0, it jumps up to 1. So for t less than 0, it takes on the value of 0, and for t greater than or equal to 0, it takes on the value of 1. And we can easily get a step of height a, where a could be any positive or negative number. It doesn't make sense to make it 0, obviously. You just multiply the unit step by a, and so then whenever it takes on 0, whenever u of t takes on 0, a u of t is still 0. And whenever u of t takes on 1, a times u of t then becomes a. So just like that. And this is a common signal because it handles this kind of idea that you've seen in circuits before, where you switch a voltage from being short-circuited like this, so that the input is 0, to being connected like this, and now your voltage is now Vs applied to our beloved RC circuit, which hopefully you remember how this thing behaves. So try to remember in your mind how an RC circuit would behave to this. Do you remember? Okay, well, we'll get to that eventually. Try to think of it, go back and review. So we can replace this whole structure here by a voltage source that is Vs times u of t. So it's a nice mathematical structure to be able to show. Another function is the unit ramp. So it's a ramp function. It starts off at 0 and then goes up with a slope of 1. So the unit now refers to unit slope. So slope, rise of 1 in a run of 1. But prior to t equal to 0, it's equal to 0. So that's a common function that shows up. And we can make the slope be equal to anything that we want. Again, letting m be equal to 0 is not such a useful thing, but any positive or negative value there. So if we were to let m be equal to, say, minus 2, then we would get something that goes down like this at a slope of negative 2. Okay, once we have a signal, sometimes we want to think about a time-shifted version of that signal. And in the physical world, time shifts are often time delays, and that's often due to the propagation of a signal. So acoustic signals propagate at the speed of sound, a radio signal at the speed of light. So that's how we use this idea to help us model what goes on in the real world. In a more mathematical way, once we have some simple signals, we can time shift them around and then add these components together to build more complicated signals, and we'll see that in just a little bit. So a time shift, suppose you know what x of t looks like. You want to know what x of t minus t0 is, where t0 can be either positive or negative. So we choose as our convention the negative sign there. So for example, suppose t sub 0 is 2, then we know that when we plug in 0 for t, so we're asking what does t minus t0 x of t minus t0 look like at t equal to 0? Well, it takes on the value of t at, or I'm sorry, of x evaluated at minus 2. So at time equal to 0, this new shifted function looks like something that happened 2 seconds in the past. So it's time shifted. Similarly, at t equal to 1, we see that the new function takes on the value of x of t at t equal to minus 1. So this illustrates that, and the two red arrows show the two cases that we just illustrated, and we're doing this for a unit step function. So at t equal to 0, at that point, the new shifted unit step function takes on the value of the old one back there. So a t minus 2 with 2 being positive shifts to the right by 2. If we had t plus 0.5, that's t minus 0.5, that shifts to the left. So when we let t0 be positive, it shifts to the right. t0 be negative, it shifts to the left. And so this little box just summarizes what we've just discovered. Now another function, the impulse function, also called the delta function or the Dirac delta function. Dirac is the name of a famous physicist who pioneered the use of this function in physics. This thing is one of the most important functions for understanding systems. We'll use it a lot more later in the course, but we'll need it every once in a while. Now, ironically, this is a theoretical function, not something that actually exists in the real world, but yet it's one of the most important functions for you to know about, because it's a tool that allows us to understand and mathematically characterize systems. But we use it all the time when we think about real world things. So our rough view of what this thing is it's a really narrow, really tall pulse, but it still has unit area. So even though it's really tall, we make it really narrow so that the product of really narrow times really tall stays equal to 1. So a little less rough view, we can nail down a rectangular pulse with some parameters. So its height here I've got labeled as 1 over epsilon, and its width, well, it goes from minus epsilon over 2 to epsilon over 2, so its width is epsilon. So its area is height times width is equal to 1 because the epsilons cancel. So no matter what I let epsilon be equal to, the area stays 1. But as I let epsilon get smaller, the height gets larger and the width gets narrower. Area stays 1, and so in the limit we say this quote-unquote becomes the delta function. There's some funky mathematics involved here in the sense that this limit doesn't really exist, but we'll ignore that for the time being. Now the precise idea to get around this issue that as you take this limit there is no real function to which it converges, the way mathematicians really think about it is they say, alright, we're going to make up some weird and wacky thing that we're not going to tell you exactly what it looks like, other than the fact that everywhere it's equal to 0 except at t equal to 0. So we think of it as 0 everywhere except at t equal to 0, but we're not going to say what it does at t equal to 0. Instead, we're simply going to say as long as you integrate this function over the point 0, you get that unit area. So remember we talked about an area of 1. And that has to hold for any epsilon greater than 0, no matter how small we make it. So that's the basic idea. So to capture that essence of something extremely narrow and extremely high, we use this symbol. So this is not, where's my, I don't even know what that is. There we go. This symbol is just an arrow. It's not showing the vertical axis. It is showing the delta function. So that's the symbol that we'll use for that. for that weird and wacky function. Now we'll stumble across this a few other times as the course goes along. Now obviously if we were to shift this, here I'm showing t positive, and it shifts to the right, and we get the delta function that's been shifted. If t were negative, this thing would shift to the left, and obviously this picture assumes that t is positive, but we could think of it as a general case. Now that leads us to this sifting property, not to be confused with shifting. This is sifting, but it does involve a shifted delta function. So if we take a shifted delta function, so now we know that this thing lives, quote unquote, at time equal to t0, and so it's it's 0 everywhere else. So when we integrate this function around the point where that delta function is, it's 0 everywhere except at that point, time equal to t0, and so it kind of grabs the function at that point. So here we're illustrating this. Remember, it's important to keep in mind that the delta function is 0 everywhere else. So when we do these products, we get 0. Now we can't really think about what happens to the product at time equal to 0 because we haven't really said what the delta function is there. But what we do know is from that area property, what it's going to do, the whole integral just boils down to just that number, the number that of the function evaluated at time equal to t0. So that's an easy thing to think about right there. Evaluate the function at t0, and this is just a seemingly very complicated way of expressing that same thing. But what's going to end up happening in our studies is, I can't get my eraser to work here. There we go. Is we will run up against things that look like this, and it'll be nice to be able to simply replace them by numbers. So that's the whole idea behind this. And I'd like to point out that this integration holds as long as the limits here surround t0. They don't have to be symmetric. They don't have to involve epsilon. Just as long as you're going from somewhere over here to somewhere over here, you're good. That result holds. So let's look at some steps for applying the sifting property. Things can get a little bit funky, but not too bad. Again, these limits can be anything as long as they're to the left and right of where t0 is. So step number 1 says to find the variable of integration. Step number 2, find the argument of the delta function. So in that case, the case we're showing, that's this t minus t0. Step 3 says take that argument, set it equal to 0, and find the value of t that causes it to go to 0. And then just as long as our limits are okay, then just evaluate everything that multiplies the delta function by evaluate it at the result from step 3. If our limits aren't correct, then we return the value 0. So the neat thing about an integral like this is there isn't any integration to actually do, and that's kind of the beauty of this thing. So here's an example. So step 1, find the variable of integration. It's t. Step 2, the argument of the delta function is t minus 1. Step 3, find the value of t that causes the argument to go to 0. That's t equal to 1. Step 4, check that t lies in our range, minus 4 to 7. T equal to 1 lies in that range. And so now finally take this part and evaluate it for t equal to 1. So I plug in t equal to 1, I have sine of pi times 1, sine of pi, and hopefully everyone can visualize sine of pi is equal to 0. No, you don't need your calculator to do that. You should know sines of things like pi, pi over 2, 3 pi over 2. Those are the easy ones, and sine of 0. And yes, we'll be working in radians, not in degrees in this course. So there's the result of that little example. Now you're probably saying, great, this tells me nothing about what I want to do with my life in electrical or computer engineering. Well, we need this as a tool. It's not very exciting right now. It's about as exciting as seeing a hammer for the first time and thinking, okay, great, what am I going to do with that? But trust me, this is a tool that will pop up a lot. Okay, so some signals that we run into are called periodic signals, and they more often than not come from some human-made device, and you've seen a lot of these in the lab. They're great for testing circuits. So we've seen sine waves, they're periodic, square waves, or at least periodic square waves, triangle waves, and things like that. So the way we define what a periodic function is for a continuous time signal, we say a signal is periodic with period equal to t if we can take x of t and equate it to x of t plus capital T, and that holds no matter where we're looking as we change the little t. So that's for all t. So here's a little picture that shows a periodic function. We can imagine this bar being slid back and forth horizontally, and it just follows vertically so that the dots are riding on this function. And so if it remains perfectly horizontal as it does that, then we say that it's periodic, and this is its period. And we'd like the smallest value of t. Obviously we could extend this over to here, and it works for that distance as well, but we want what's known as the fundamental period. So there's another picture of it slid over to another point, and you can see that the relationship holds there. So the fundamental period, as I said, is the smallest such t, and we almost always leave off that cumbersome fundamental at the beginning and just simply say period, and everyone knows we're talking about fundamental period. Okay, so we've got some signal. Say it's a voltage, and we're interested in measuring how powerful this is, how big it is in some sense. So in a physical system or physical circuit, if this x of t is a voltage and it's dropping across a resistance, we know from our circuits class that its instantaneous power is voltage squared over resistance. So we can write the instantaneous power P of t like that. Now, in this class, we often don't have a specific circuit or system in mind. We're just trying to come up with a measure of a signal in and of itself. So we often just ignore this R, or effectively set R equal to 1. So we can think of this as a normalized power, but we generally don't even bother with that idea. So we can always convert it back by dividing by the appropriate R. So now, if you recall that power is actually the rate of energy, so it's energy per unit time, so that 1 watt is equal to 1 joule per second, that tells us that the instantaneous power is the derivative of the energy as a function of time. Now that also tells us that a differential increment in energy would be equal to the instantaneous power times the differential increment in time. And so now this sets up a nice integral for us. So then for a periodic signal, we can find the amount of energy in one period by just simply taking and integrating from any time to another time that's a period away from it. And what are we integrating? The instantaneous power times, well, we don't physically think of it as times the differential that's in the integral, but the differential is, the time differential is what converts that power into an energy. So that gives us a way of coming up with the energy in one period for a periodic signal. Now, since the periodic signal goes on forever, if we were to integrate from minus infinity to infinity, we would keep getting that amount of energy repeated infinitely many times. So we can see that the total energy that is delivered by a periodic signal would be equal to infinity. Now, if the signal's not periodic and the signal kind of trails off both as t goes to negative infinity and as t goes to positive infinity, if it trails off fast enough, then this integral may be finite, and we would say that that signal has finite energy. So again, recalling that power is equal to energy per unit time, if we were to find the energy in one period of a periodic signal, which we just found, and then divide it by the amount of time there is in one period, we would get the average power in one period. We often just call this the average power of the periodic signal, and we would use that formula to compute it. So for periodic signals, we can use this concept of average power as a way of measuring the size of the signal. So for practical periodic signals, the average power is finite but not zero, and the total energy of the periodic signal is infinite, if you remember from our previous example. Okay, moving on to another subtopic here. We define a rectangular pulse function. So we're going to reserve this notation for the idea of a rectangular pulse. The subscript tau tells us the pulse width, and by convention the width is tau, but we're going to say it starts at minus tau over 2 and goes to plus tau over 2 with a height of 1. So that's what we mean when we see that symbol. Now we can build that very easily from unit step functions, and we just have to take a unit step that turns on here and then subtract off one that finally turns on over at this time. And so there is the one that turns on. So that's the first function, and then that's the second one. And what we're going to do is subtract these two things. So when we subtract 0 from 0 in that time range, we get 0. That's what we have up here. In the next time range, we've got 1 minus 0, and that gives us the 1 that we see here. And that holds all the way up to here. Now we have 1 minus 1, which is 0 again, and this drops back to 0. So this way of building things with the unit step is a very useful thing, and you should practice and make sure you understand how to make a rectangular pulse function, but try with other combinations of unit steps there to create other kinds of things. So once we have a pulse like this, or we could do this more explicitly with unit steps to turn things on and off, but we want to use this to mathematically build up some model for some signal. So here's an idea. Suppose we start with a line that has a slope of 0.5 and a y-intercept of t. I say y-intercept, so it goes y-intercept of 1, so it goes through 1 with a slope of 0.5. But this thing keeps going up, come on, draw, and keeps going down. Okay, that's not really the kind of signal that we would find in the real world, but we might find something that has that slope, but only for a short period of time. So we can actually take a shifted version of our rectangular pulse. So p sub 2 tells us its width of 2. We're shifting it by 1, so that brings its edge over to here. And so what this thing does is, if we multiply this pulse times this line, out here the 0 is going to basically convert all those to zeros. Then the 1 in here is going to allow that thing to be itself, and then the zeros out here will convert that to 0. when we multiply. And so the result would look something like this. So here's the result of that. And that's a nice little way of illustrating how we use mathematics to formulate an equation, a math model for some sort of little pulse that we might imagine occurring as an input to a system. So as we go through the rest of the course, we'll have plenty of opportunities to build little signals this way, so keep this idea in mind. Thanks.